Hello everyone, welcome back to another video tutorial in strength of material. So in this video, we will talk about shear stress in beam. Okay, so again, when we say shear stress, based on the perspective of an actually loaded structure, a shear stress happens when we have a force that is acting parallel on the surface area. Okay, on the surface of our structure. Now in the beam, we have a shear stress when we have shear force that is parallel on the cross-sectional area of our structure. So if we have a shear force, we will have a stress on this surface, so that is the parallel. So we would have shear stress or in the cross-section, as well as there would be shear stress in the longitudinal axis or longitudinal length of our structure, like just this one, and this is equal. So if we have a load P that is acting, so there would be stress on this axis here, okay, on this area, across this area here. Okay, so therefore our shear stress is expressed in this formula, that is the shear stress is equal to the shear force. Okay, this is the internal shear force, and we have Q here, that is the moment area, that is 8 times Y. Our Y here is the distance from the centroid of that area to the neutral axis. And then we have I here, that is the moment of inertia, and B, that is the width of the shear area. Again, Y is the centroid of the area of the section to the neutral axis. So this is the formula for horizontal shear stress, or the shear stress occurs that is in parallel to the longitudinal axis of our beam. Okay, this one here. Take note, this is the cross-sectional area. Now in beam, the maximum shear stress occurs in the neutral axis. Okay, now this is in contrast with the flexural stress. When we say flexural stress, the maximum stress occurs on the outside surface of the beam, but in shear stress, our maximum shear occurs on the neutral axis. Okay, if we have rectangular beam, our neutral axis is on the center, or that is h/2. Now if we have a built-up member, or if we have member that is fabricated separately and they were combined to form a member or a beam, then they are connected by a rivet or a bolt, correct? Now we can compute the spacing of that rivet by using this formula here, S equal to RIVQ, where R here, this is the shear force capacity of a single rivet or bolt. So we are going to compute for the spacing of a rivet if we have a built-up member. Now, if for circular section, as what I have mentioned, our Q here, that is our area times the centroid to the neutral axis, barred Y times A. Now, for circular member, we might find it very difficult to compute for Q, so we have given formula here, that is, we have 4R over 3 pi here, that is the location of the center of our semicircle to the centroid or center of the entire circle, that is 4R over 3 pi. Okay, or by further simplifying this expression, we could have 2 over 3 R raised to the 3. So you can familiarize this one, but if you forget, you need to also to learn this how to derive. Okay, now for a tube, okay, we have a hollow. We just need to minus the moment area of the bigger circle and the smaller circle or the hollow. Then we have 1 over 12, that is the outside diameter cube minus the inside diameter cube, or we could say that is 2/3 R cube. R here, that is the radius from the center to the outside surface, minus R cube, that is the center to the inside surface. Okay, so you can just memorize this formula here, or it would be better if you know how it came up with this expression. You need to familiarize, or you need to understand this concept, the concept behind, so that in case you forget this expression here, you know how to derive. Okay? So it's for a circular section and computing the moment area. Now let's try to solve problem. Okay, we have a problem here that is a 3.2 meter long simply supported laminated wood beam consists of 8 40 mm by 180 mm planks glued together to form a section 180 mm wide by 320 mm deep, as shown. The beam carries a 45 kN concentrated load at midspan. At section A, located 0.8 meter from support A, determine the average shear stress in the glued joint at B, C, and D. Then, the maximum average shear stress in the cross section. Okay, we have built up section here. Remember, we have 8 40 mm by 180 mm that are combined. Okay, they are glued at this section here, and then they are combined to form a one member or a one structure. Okay, take note, this is 180 mm by 40 mm. Okay, now we know that we have a 3.2 meter long simply supported beam, and this simply supported beam is under or carries a 45 kilonewton concentrated load at the midspan. So we have 45 kilonewton at the midspan, that is 1.6 meter from both ends. Okay, now we are asked to compute for the shear stress, okay, at section AA located 0.8 meter from support A. Okay, so if we have this our A, this our B, so we have 0.8 meter from A. Now if we cut our section at AA, then we could have our shear force here exposed. Okay, that is V. But first, before we compute for our V, we need to compute for the reaction first. Now, since this is a symmetrical beam, okay, our 45 kilonewton is acting on the center or on the midspan. So therefore, we have our reaction at A and B is just 1/2 of 45. Then we have here 22.5 kilonewton that is at A, then we have 22.5 kilonewton which is acting at B. So therefore we have 22.5. Now how are you going to compute for V? You can use either moment equation or shear and moment diagram. But since we do not have a force acting from A to section AA, then we could say that our A here, our reaction at A is the same as or equal to our internal shear force. Since if we cut that section, let's say this is our section AA, we have at A that is 22.5, then we have shear force here, then we can just sum up forces, vertical is equal to 0, then we could have our V that is also equal to 22.5 kilonewton. Okay? So we have now our internal force at section AA that is 22.5. Now we can proceed to the average shear stress in the glued joint at B, C, and D. So we are asked to determine the internal or the average shear stress at these points. Okay? So let's try to solve point B first. We have at point B. Now we have the formula for shear stress that is equal to VQ over IB. Correct? Now our V here is the internal shear which we have already computed. Now V is 22.5 kilonewton. Okay? Now we have to compute for our Q. Q is A times barred Y. Again, our A here, that is the area, and this area here is above to that point. Now if we have this our B at this point, so therefore the area should be this one. Okay, so therefore we have our area or Q that is equal to, that is the area of the shaded region, that is 40 times 180, that's the area. Now the barred Y here, now we have to locate first our neutral axis. Since this is a rectangular beam, now 320 divided by 2, we have 160. So our axis is located, that is half of 320, that is it's 160 from the bottom and top surface. Okay, since this is a rectangular beam. So we have now our barred Y, that is the centroid, this one here, to the neutral axis. That is, we have 160 minus the distance from the top surface to the centroid, that is half of 40, that is 20, correct? So therefore minus 20. Then we have 160 minus 20, that is 140. So therefore we have barred Y, that is 140. Okay? So we have Q here, that is equal to, that is 1,008,000. Okay, now this is in area is in millimeter squared. Our barred Y is in millimeter. Then we have the unit, it is millimeter cube. Okay, that's our Q. So we can now use this value here to our formula. Then we have the shear stress equal to our V, that is 22.5, is 22,500. So we convert it into Newton, times our Q, that is 1,008,000. That is millimeter cube, over our I here, that is the moment of inertia. Since this is a rectangular beam and symmetrical at both axes, then we have 112 BH cube, correct? So 1 over 12, our base is 180, our height is 320 cube, times, and the unit is in millimeter to the fourth, correct? Then times our B, that is the width of our shear area. Now our shear area is this one, this shaded region here. So therefore our base width is 180 millimeter. So we have the answer here, which is equal to 0.256. Now the remaining unit is, since we can cancel this millimeter cube here, okay, and then millimeter to the fourth, the remaining would be in the first, okay, since we can cancel out 3. So therefore we have unit that is in Newton over millimeter squared. Since millimeter times millimeter, then we have millimeter squared. So therefore we have the answer, that is 0.256, that is in megapascal. This is the shear stress at point B, okay, at this point. Now we are asked to compute for the shear stress at point C, okay, using again this formula. Then we have our Q, that is A barred Y, wherein our A here, again, that is the shear area. Now since we are asked for point C at this point here, so our shear area would be different from the shear area of B. So that is, the shear area is above point C, that is this one, okay? So our area, that is equal to 180 times, we have, since this 40 plus 40 and then 40, we have 3 wood, that is 40 by 180 mm. So therefore we have 120. So the total is 120. It's the area, this one is the area, times the barred Y here, that is the centroid of this area to our neutral axis. That's a barred Y. So we have our barred Y, that is equal to that is 160, correct, the entire height from the neutral axis, minus this height here, that is 1/2 of 120, that is 60, correct? So therefore we have 160 minus 60, our barred Y is equal to 100. So we have here times 100, and we have Q, that that is equal to 2,160,000, that is in millimeter cube. Correct? So our shear stress is equal to our internal shear at section AA, that is 22,500 times Q, that is 2,160,000 over our I. Our I, since this is a rectangular, 112, 180 times 320 cube times our width of our shear area, that is 180. That's the base width. So we have our shear stress, that is 0.549, that is in megapascal. So as what you can observe, the shear stress at point C is greater compared to shear stress at point B. So as we are approaching towards the neutral axis, our shear stress is increasing. Okay? So therefore, our maximum shear stress here occurs at the neutral axis. And lastly, we have at point D, and we still are using the formula that is VQ over IB. Okay, our Q here becomes our area, the shear area, since our point D is below the neutral axis. We can use this shear area here, okay, or the shear area above D. We can also use this area. Okay, either way, we should come up with the same answer. Okay, but I'm going to use here the area below point D. So we have the area that is, again, that is 180 times, that is 80, correct? Since we know that is 40 and this one is 40. Times barred Y, that is from this point, the center of our 180 width or height, that is to the neutral axis. We have 160 minus 40. Okay, so therefore we have 120 as our barred Y. So we have our Q here that is equal to 1,728,000 cubic millimeter. Okay, so our shear stress equal to V, the shear area, 22,500 times our Q, 1,728,000 over I, that is 1 over 12 base 180, height is 320 cube. Then the base of our shear area, that is 180. And the shear stress gives us 0.439 megapascal. Therefore, this is the shear stress at point D. Then question letter B ask us to compute for the maximum average shear stress in the cross section. Again, the maximum average shear stress occurs on the neutral axis. So we still have the formula that is VQ over IB. Okay, our Q here, since we are looking for the stress at this point, the neutral axis, so our shear area is this one, in which our area that is 160 times the width, that is 180. Then we have our barred Y, that is from the centroid to the neutral axis, or that is just 1/2 of 160, then it gives us 80, correct? Then we have our Q, that is, and then we have our Q, which is 2,304,000. Then we're gonna use this value in our formula. That is, we have our V, that is still 22,500 Newton. Our Q is 2,304,000. Okay, over our I, that is 112 base 180, then H cube, which is 320 cube times our base of our shear area, that is 180. So this formula gives us the maximum shear stress, which is equal to 0.586, that is in megapascal. So this is the maximum shear stress which is on the neutral axis of our cross section.